In Laguna Lake's pristine waters, a hidden menace threatens marine life, the microplastics. As aquaculture flourishes, plastic pollution surges. Enter ferrofluid-based, our innovative solution to combat microplastic contamination. Join Ace Cordova, Maria Alexa T. Postrado, and Daniel Jan P. Tocmo, mentored by Ma'am Crisalin Ariola and Sir Michael Gabat, on a mission to protect our aquatic ecosystems with an automated ferrofluid-based system. This is not just a research, it is a call to preserve our oceans for the future.
The thriving aquaculture industry, supported by 824 bodies of water, boosts the Philippine economy. However, plastic pollution, notably in Laguna Lake, is a growing concern according to Arcadio et al. 2022. Microplastics from plastic breakdown and industrial runoff pose a long-term threat to the Philippine marine biodiversity. The Philippine Clean Water Act of 2004, also known as the RA 9275, underscores the urgency for environmental protection, mandating measures for water quality improvement. Previous studies explored the ferrofluids for application in electronics, leveraging their dynamic properties for controlling fluid systems.
While ferrofluid technology shows promise in reducing riverborne microplastics, research gaps persist, emphasizing the need for improved recyclability and reduced environmental impact. Our study, Ferrofluid-based, addresses these gaps, aiming to create an automated ferrofluid-based system for efficient microplastic removal in sun and river, to safeguard our oceans, benefiting consumers, society, and future researchers.
Now, let's explore how ferrofluid-based will address this microplastic challenge in the San Juan River through a meticulously designed methodology. Spanning 7 phases, this process articulates how ferrofluid-based is crafted and tested. Phase 1. Materials collection. The researchers gather the necessary materials such as vegetable oil, magnetite powder, and clear plastic containers for ferrofluid preparation and water sample experiments. Microscopy and Adobe Photoshop for data analysis were used to identify the microplastic concentration. Phase 2. Sample collection. The researchers used data from the Santo Tomas Community Environment and Natural Resources Office to identify the San Juan River watershed location for water sample collection to ensure an accurate assessment of environmental conditions and potential microplastic contamination.
Phase 3. Synthesis of ferrofluid solution and flowing river model assembly. Using 0.5 ml per 0.5 liters of vegetable oil and 1.5 grams per 0.5 liters of magnetite powder resulted in the highest microplastic retention and removal efficiency after testing for a specific plastic to oil and plastic to magnetite powder ratio. The flowing river model was also assembled and Arduino Uno was utilized for the system's automation. Phase 4. Introduction of ferrofluid treatment. The researchers carefully added the meticulously prepared ferrofluid to the water samples. Phase 5. Setup assembly for physicochemical screening of water samples. Microscopy, initial reading. Researchers employed microscopy and Adobe Photoshop to quantify the microplastic contaminants in water samples. Microscopy using microscope provides detailed information on dimension, morphology, and composition of the microplastics. In Adobe Photoshop, using a specific color range, the researchers calculated the plastic percentage by assessing the coated pixels.
Phase 6. Physicochemical screening of water sample, microscopy, post-treatment. Researchers quantify microplastics drawn and retained by ferrofluids and assess their impact on microplastic concentration. Using microscopy and Adobe Photoshop, the remaining microplastics are measured. This analysis aims to evaluate the efficacy of ferrofluids in reducing microplastic concentration in the water sample. Phase 7. Data analysis and interpretation. In this study, researchers synthesized ferrofluid without stabilizing agents or surfactants for the removal of 3 to 5 mm polypropylene microplastics in a 500 ml water sample. The ferrofluid, composed of oil and magnetite powder, underwent variations in vegetable oil concentration and iron oxide dosage to optimize microplastic removal. The study found that a consistent ratio of 1.25 gram of magnetite powder to 0.5 ml of oil per 500 ml of water yielded the highest microplastic removal efficiency. Specifically, using 0.5 ml of oil per 500 ml of water was identified as the most effective condition. Subsequent trials demonstrated consistent removal efficiency with a 94% reduction in microplastics. These results emphasize the efficacy of the synthesized ferrofluid in microplastic removal and highlight the importance of carefully balancing oil volume and magnetite dosage for optimal performance.